Thank you very much. Morning, everyone. I'm Pete Burnap. I'm Professor of Data Science and Cybersecurity at Cardiff University. Essentially, I lead cybersecurity research, and the talk today, co-delivered with my colleague Matilda, is essentially going to be around how we use AI to improve cybersecurity. And very specifically, we're going to focus in on how we've achieved impact through working with one of our strategic partners, Airbus. So a whole bunch of stuff essentially to start off with around what we do and why we do it, and then we'll drill into a little bit more around how we've actually used AI to innovate and to integrate that within Airbus, who obviously have a huge cybersecurity interest, as should most people in the room, I would imagine. So, just to give a bit of context, background, so the UK and most developed nations have a cybersecurity strategy, which is pretty much to keep the country safe and resilient to cyber attacks. In the UK, there was a huge investment over recent years, £1.9 billion in investment in preparedness and resilience, and part of that was to set up the National Cybersecurity Centre. So the National Cybersecurity Centre have a remit to keep the UK safe and also active cyber defence, which essentially means seeking out cyber threats and dealing with them, taking them down, things like phishing pages and malicious web servers. So also in the UK, we have an industrial strategy. The industrial strategy, as pretty much everyone in the room will know, has a core sector deal or focus in AI and the data economy. So this puts AI at the forefront of the UK economy. So essentially at Cardiff, in our research and with our strategic partners, what we do is we fuse those two things, AI and cybersecurity. And we're pretty much working in the area of the remit of the National Cybersecurity Centre, which is seeking out, detecting threats and doing something about them. So the National Cybersecurity Centre have 17 academic institutes in the UK who they have accredited as academic centres of excellence in cybersecurity research. This essentially means that we meet the criteria around excellence in publications, PhD track record, external funding, that kind of thing, and have a core strategic vision, which is one of the major foci. So our strategic vision has been framed around cybersecurity analytics, which is this fusion of AI and cybersecurity. We achieved this accreditation last year, and the reason the trophy is on the side there is because that's essentially the nature of this talk. We've received awards for our innovation at an international level with Airbus. So, just to give you a brief overview of the kind of areas we're working on, because this is all very relevant to AI, and this kind of slide pulls a lot of the stuff that we do together into a single slide. So, across the university, we have 38 researchers working in cybersecurity analytics. As you'd imagine, a lot of those are in Department of Computer Science, but we also have probably half of those in other disciplines, including criminology and psychology. Particularly, psychology is an area of growth for us. And the reason for that is because both AI and cybersecurity are very socio-technical problems. There's absolutely zero chance of us achieving anything sustainable or with real impact by working as computer scientists on our own. So these kind of topics pull together the areas that we're working on. I'll just give you a brief overview before I hand over to Matilda to talk you through some of the detailed tech stuff we've done in AI. So the first, over on the far side, is risk assessment and modelling. Now, traditionally, risk assessment is very much, here are our risks, and they're based on threats, vulnerabilities, assets, putting them together in sort of a matrix, perhaps a spreadsheet, maybe getting some accreditation from ISO or something similar, and then sticking it on the shelf. But this is not particularly useful in a world of ever-changing cyber threats or ever-changing threats full stop. So we've done a whole bunch of work around goal-oriented risk modelling, which essentially takes the perspective of what do we actually need to go right rather than what could go wrong. We've done a whole bunch of workshop-based stuff plus a methodology, and including the development of a tool that allows us to collect dependencies, starting with a higher level dependency. What does the organisational aim to achieve? And then you ask the iterative question, what does that depend on? What does that depend on? What does that depend on? And so on. And you end up with a top-down tree of dependencies, which actually then lends itself pretty well to probabilistic modelling. So you can actually say, if something changes way down here in the supply chain, how does that knock-on effect right up through the organisation, right on through the supply chain, which actually in a globally interconnected world is very important. These is web-based, and so you can actually share this information between companies, and as one company's probabilities of success change, that can be propagated. So a whole bunch of stuff around that. Bit in the middle is around risk communication, which is very important, decision-making, how people make decisions, why people make decisions, and the bit running right across the top feeds into that, which is the human factors. So why do people behave securely or otherwise? Why do people make, or how do people make decisions in scenarios such as, I'm receiving this information from an AI that's telling me that there's an attack going on. So a whole bunch of stuff underneath that around how people need to ask questions, interpret the outputs of AI, and also interpret or feed into, for example, machine learning features, some of these aspects around what would we expect to see in a cyber attack. If we're using machine learning to detect some of this stuff, what would be the motivations, the social dynamics, the kind of things that we'd expect to see. So that feeds into there quite significantly. The third pillar is then around AI, fundamentally machine learning largely to detect and mitigate different types of cyber attack and give us what we term cyber situational awareness. You'll notice then that the line goes right back around to risk assessment and modelling. So what we're actually doing is working on methods to be able to detect attacks and use that information in real time to feed a goal-oriented risk model. So rather than just saying there's an attack, we can actually understand how that attack is likely to impact us, and Matilda will talk around how we can use that kind of data to make decisions. The bit cutting through all of it is emerging tech. So security of mobile, security of IoT, security of cloud, and going forward, security of connected vehicles, for example, but also security of AI itself. So as we well know, there's a whole bunch of work emerging on adversarial AI, trying to manipulate the decisions of AI based on changing the input to it. So actually securing AI is a big thing for us going forward. So I said that I would focus on some of the industrial applications, and I will do now. You'll notice a whole bunch of things we're involved with. Most importantly for the people in the room would be, first of all, Petrus. So Petrus, for those who don't know, is the National Centre of Excellence for IoT Cybersecurity. It's led out of UCL and has 12 university partners. So Cardiff's co-leading the safety critical systems aspects of IoT. So how IoT is converged with industry control systems, and we're using, that becomes one of our emerging tech, if you like. So we're using attack detection methods and risk assessment models for that. Then I'll mention the Airbus Centre of Excellence in Cybersecurity Analytics. So this centre was set up 3 years ago. I was seconded to Airbus, so they're 15 minutes down the road is their European cybersecurity headquarters, which is quite lucky. So I was seconded there to lead what they termed AI for cybersecurity. We've since sort of turned into cybersecurity analytics, which is the fusion of AI and cybersecurity, but makes more sense internally within the business. People can get their heads around it. It makes a lot more sense what that's about. So the remit there was just to shape some ideas and some proposals, and which we did. And some of those are around malware detection using machine learning, malware prediction using machine learning, and understanding the outputs. So over the last 3 years, the team has grown to have now 4 staff members and PhD students from the university on site for multiple days a week. So the previous speakers mentioned co-location. I think this has been really crucial to some of the success that we've achieved, because we've got a strategic view of where we want to go as a university, as a research group, that matches Airbus, is that we've co-created and actually managed to get us all on site a couple of days a week. So rather than having quarterly meetings where we report on projects, we're actually co-creating the projects day in, day out. So this has been really important. As a result of the successes of that, we transferred 2 technologies into the business that are now being used within this cyber incident response teams and security operations centres. Hence the setting up of an Airbus Centre of Excellence in Cybersecurity Analytics at Cardiff University. Now this has allowed us to leverage a whole bunch more funding and actually deliver a whole bunch more stuff to Airbus. So the message to the room essentially is, as I hand over to Matilda to talk about some of this stuff, this is what you can achieve if you actually co-locate academics, both senior academics, early career researchers, PhD students and postdocs, and commit to what is essentially a 3-year project. We're now extending it for a further 3. These are the kind of things that you can achieve through that kind of co-location and shared view. So I will hand over to Matilda to talk some more.
Hi, so thank you for your time. My name is Matilda. I'm a PhD student at Cardiff University, and I'm funded by Airbus. So I spend half my time at university in Cardiff and half my time at Airbus in Newport in the cyber operations team doing research with them. I'm going to talk a bit about some of the AI solutions that we've been developing that are now being pushed into the business. And what we've been doing is trying to detect malicious software using AI and machine learning. So there are some really big challenges in this sphere. One of them is getting hold of data. That's something that anybody who's working on machine learning here will be familiar with. But in the cybersecurity world, the data moves because the incentives and the challenges for the malware authors, for the adversaries, change. So different malware families come into prominence over time. So your data set goes out of date very quickly, and you need a huge amount of it. This sticky tape broke. And getting hold of that can be quite difficult, particularly in academic setting. So that's something we've benefited from working with a large organisation. They have a huge amount of data. But because we are academics, we also freely publish our work, we publish our data sets, we put our code online, and that is something that internal industrial research teams don't commonly do. So attackers are highly incentivized to evade your automatic detection, and the detection needs to be automatic because we see about 700,000 new distinct malicious files every single day that need detecting. There are not enough security analysts to look at these, and even if we did have enough analysts, the malware authors would just create more so that you would be flooded. So this system needs to be automated, and it needs to be future-proofed. The traditional way that we would detect malware is some specialists look at malware we've seen before, they identify particular signatures, snippets of code, and create a big kind of database of what they know is out there. So this isn't going to work when we get a new piece of malware because it's not going to be in our big database. And also, we can quite easily tweak some existing piece of malware so that it doesn't match the database anymore. Anybody here who's ever written a computer program knows you can write it a million different ways and it will do basically the same functionality. But when a malware enacts its malicious activity, it has to exhibit some particular behavior. So if you want to steal 3 terabytes of data, you have to move 3 terabytes worth of packets wherever you need it to be. This is basically unavoidable for the malware because it's intrinsic to how it works. If you took that away, it wouldn't be malicious software anymore. So researchers realized this a while ago, and they started doing this behavior-based analysis. So this is where we execute the malware, typically in a sandboxed, virtualized, safe system, so it's not connected to the network. We see how it behaves, and we use that to create rules or train machine learning AI models to detect malicious software. The problem with this approach is that it can take quite a long time. The data that we used for this is listed here. So we have things like the total number of processes, the CPU usage, the memory usage, and the packets being sent around. The reason we chose these pieces of data is because every single program that executes, almost every single one, will exhibit some activity constantly along these metrics. So even if it's not using the CPU, which it then is kind of asleep, I guess, but it's still using a tiny bit, there's always going to be some metric coming out. So every second we poll these pieces of data for 5 minutes to see how the malicious software is behaving. And what we want to do is use that data in order to classify all of these different malwares. So this is however many is in that grid. All of those represent a piece of malicious or benign software. Humans are very good at computer vision. Computer vision is one of the most successful areas for deep learning and AI. If these were all pictures of different animals, you'd be able to tell me what they were. Even a security expert can't look at these at a glance and say, oh yeah, that's ransomware, that's spyware, that's Microsoft Word. So how can we tell the difference between them? What we were interested in doing was building a tool for the Airbus Secure Operations Center analysts. So this was a requirement that came from the business, and it was, when we get a new sample in, can we tell if we've seen something like this before? Because often large companies will have targeted campaigns that are coming in, so they have a huge number of samples coming in, they need to know how to prioritize. Can we DNA profile the malware to find the closest matching relative to the incoming piece of software? Is it something we've seen before? And then we can say, okay, that's fine, put that to one side. Let's prioritize the really new stuff. So as if you did a DNA test and you had a lineup of 100 people and you had to find your closest relative of that lineup. The way we did this was using self-organizing feature maps. So this algorithm maps from a high-dimensional space to a low-dimensional space. So you can map it into 2D, which means you can see it easily, visualize what's going on. So that's just a toy example with colors. The data is the red, green, blue channels of the colors, and the self-organizing feature map will reorganize that data into two-dimensional space, and it clusters similar behaviors close together. So how does that work in a malware context? This is an unsupervised learning algorithm, so we train two separate maps. The green one on the left has seen thousands of examples of benign software, and the red one on the right has seen thousands of examples of malicious software, and organized itself to group similar behaviors together. The brightness of the nodes in these two maps indicates how often we saw these behaviors. So a really bright hotspot means we've seen these behaviors a lot of times and they're similar to one another. So this is a helpful tool for the analysts because they can then interrogate those areas and see how malwares are behaving similar to one another. So once we have our maps trained, we can then feed in a new sample. So imagine this sample is executing in the back in the virtual machine. We find the closest DNA relative on one of these two maps, and we can plot the behavior. And this is a tool that is now being used in the Secure Operations Center by Airbus. I mean, it doesn't flash for them. It's a bit more slick because that would be very annoying. And we can see by looking at it sequentially, even though it's lighting up the good map a little bit, we can tell that it's mostly hitting on the bad map. This data is then fed into another algorithm, a logistic regression, and it means we can translate all of our original data into malicious or benign to get a final result, as well as that analysis. The analysts can then, as I said, interrogate the map and find out what the particular node means. So this one might mean very low memory use and very low CPU, and to those experts, that will indicate particular type of malicious software is running. Now, this approach is really useful for the analysts, but as I said before, it takes 5 minutes for a single sample to execute. And that's once it's already reached the network. And what's really useful with a cybersecurity attack is if you can actually detect it beforehand and stop it from running in the first place. So we wanted to see if we could take all this data that we'd painstakingly collected and use it for another use case within the business for detecting malicious software. So 5 minutes is too long for anybody to wait for their antivirus to analyze a file, according to user experience research. So we wanted to see how quickly can we predict that a file is malicious or benign, even when it hasn't actually executed the malicious payload. The way we did this was using a recurrent neural network. So recurrent neural networks can process time series data. So we take that big image of how the data is enacting over time, and we use it to train a model. And what we found was that after 5 minutes, the average that the literature uses for classifying a sample using this behavioral approach, we got 98% accuracy. But after 28 seconds, we also had 98% accuracy already. And after just 5 seconds, we had 94% accuracy. So we could actually plot a little curve of your trade-off. How strict can you be with your employees? How likely are your employees to turn off their antivirus if it takes too long? And how accurate do you want the model to be? So we can also get a prediction every second as to how confident we think the model is. I don't know if it's too dark to see, but the kind of wedge of the pie indicates the confidence. So it gets more confident over time, and that makes sense because the model has more data as well. So around the time that we built this model, the WannaCry attack hit the world, and notably in the UK, hit the NHS very badly. And we wanted to see, would this have worked as a detection system on ransomware and other families? So what we did was we hauled out all the malware from a particular set of families and just trained it on some quite old data and saw, is it able to detect these families that has never seen before during training. And what we found was that it was able to detect 99% of the 2,500 ransomware samples we gave it within 1 second. So that was good news from our perspective. And it's actually because ransomware is an extremely unsubtle piece of malware. You know, it's like barging right in there, encrypting all of your files. So it made sense from that perspective, but obviously the system wasn't in place. And now this is being compared against existing security solutions at Airbus to see if it could be rolled out to be used on endpoints within the organization. Finally, I wanted to include some recent research we've done, which I think will be interesting to this audience. We are presenting this paper at DSN conference in a couple of weeks, and the title was Lab to SOC. That was before we got invited here on the Lab to Live stage. It's literally about the same thing. So we painstakingly gathered all of this up-to-date malware and benignware data from the wild. So just went on every dodgy website, well, a crawler did that, and downloaded all of this terrible stuff, which we used to train our model. But with this work in our environment in Airbus, so what we collected was another data set which came directly from our SOC, so all the malware that they detected and all the safe benign programs. And what we wanted to see is, does the data that we've chosen, that machine activity data, CPU usage, bytes being sent and received, does that stand up to API calls, which is what most people are using in research to detect malware? There's a reason we didn't choose it in the first place. API calls are functions made to the operating system, basically saying, please, can I have some memory to run this process? Can I create a file? These get depreciated over time. The way that programmers' code changes over time, particularly malicious authors, as I said, various carrots and sticks come up that make malware migrate the type of malware that is popular. So we didn't use them. And what we found was that our machine activity data stood up better across the two different data sets. So this is an issue of concept drift that you can get when they don't stand up. So the blue is our test data in the wild that we collected, and the orange dots are our organization collected test set. So the machine, and we tried it with 3 different algorithms: random forest, support vector machine, and neural network. And if you can see on each 3 of those graphs, the leftmost column, the blue and orange dots are highly clustered together, whereas the orange dots, the real-world data from our organization, scored much lower accuracy, in some cases less than 60%, when it was sometimes achieving, you know, high to mid-70s or mid-80s going down to 60%. And that would be terrible, particularly in the case of a neural network where it's kind of a black box. We have some degree of being able to explain it, but we've told our clients, you know, this is the accuracy it's getting, and that's what they're depending on. And then with their data, it isn't working. And these are the kind of tests we like to see more of, and it's something that we were forced to do because of being embedded in a real organization. It's not a typical part of research that goes on. So I'll finish by just saying a bit about academia and business. I don't know if there are many academics in the audience, but I'm sure there are lots of people from industry. I'm a PhD student, and I have had some amazing opportunities which other people in my department who are not sponsored by an industry partner have been given. Things like being able to speak here, networking opportunity, media training, all kinds of networking opportunities, and working with a real team of employed researchers who work on that shorter industrial timescale that works really well when you complement it with academic partners who might be going a little bit more blue sky. We found that that combination works really well in Airbus. So those have been a lot of the benefits from the academic side, on top of impact being built into every project we do right from the beginning, which is the metric by which we're now measured in academia as well. From the industry side, I would say that adopting a PhD student is a good idea, because you can train them up. You can make them a kind of semi-employee so that when they come out of their PhD, they're ready to go straight into the business. They haven't been working in this slightly different world where the rules are different and the deadlines are longer and the ideas are more blue sky, which is always important, but we want to see impact in the real world as well. I think that's everything I have to say. So thank you from both of us. And